Welcome. In this video, we tackle section 3.11, Related Rates. Fun word problems, where two quantities change over time. Here is the setup. Two quantities change over time, and the quantities are related. For example, the area and radius of a growing circle. Imagine that circle is growing, its area changes, and its radius changes. Or side length and volume of a cube that is shrinking. Or two ends of a ladder that is sliding down a wall. In each case, there are two quantities. Both of those quantities are changing, and so their rates are somehow related to each other, the rate at which the two of them change. To find out how their rates are related, here's what we do. We find an equation that relates the two quantities, then differentiate the equation with respect to time. I imagine that each of these two quantities is a function of time. And so when I differentiate with respect to time, it'll give me an equation that shows how the rates are related. Let's do some examples. Waves in a pond. A rock is thrown into a pond, and the ripples move out at, say, 3 feet per second. How is the area of the disturbed water changing after 4 seconds? So here's the strategy we will follow. Find an equation relating area and radius, differentiate both sides with respect to t, and then solve for dA dt. Now, dA dt, let's remember, that is the rate at which the area is changing. And that is what I really wanted to find out from the problem. How is the area changing after 4 seconds? Okay, let's begin. Find an equation relating A and R. Well, it's a circle, and I have a radius, and that circle has a certain area. So how about A equals pi r squared? I've related the two quantities. Next, differentiate both sides with respect to time. So I think of A as a function of time. When I take its derivative, I get simply dA dt. Now let's take the derivative of the right-hand side, and I think of r as a function of time, r as a function of t. So pi is a constant, pi, I take the derivative of r squared, that becomes 2r, so to the first power, then by the chain rule, dr dt. So look what I have dA dt on the left and dr dt on the right. Those are the rates. Those are the rates of change. And so now I have related the rates. At this point, we can try step number three, solve for dA dt using any extra information. So let me put a box around that. That's what I want. So I need to put in numbers for every other variable that I see. So what about the dr dt? What is dr dt? Oh, that's the rate at which the radius is changing, and I look up at the problem, and I see it right there. That's 3 feet per second. 3. What is the r? So that's the actual radius. How is the area of the disturbed water changing after 4 seconds? I don't want to put 4 in there, because 4 is a measure of seconds. So I need to figure out what is r at 4 seconds. The ripples move out at 3 feet per second. After 4 seconds, 3 times 4, that'll give me 12. 12 feet. Okay, so I'm going to put 12 in for the r. Okay, so I have put in numbers for all the other variables, and the only thing left is dA dt. So dA dt equals pi times 72. All right, so 72 pi. And 72 pi turns out to be approximately 226.2. What are the units on that? I'm looking at dA dt, so A is measured in square feet, time is seconds, so square feet per second. And there's the answer to the problem. Let's do another. Here is a classic problem that is probably in every calculus text. The falling ladder problem. A 16-foot ladder slides down a wall as its base is pulled away at a constant rate of 3 feet per second. So we see the picture here on the left and the arrow. So the base of the ladder is being pulled away at a constant rate of 3 feet per second. While the base is being pulled out, naturally, the top is going to slide down. So here's the question. How quickly is the top of the ladder sliding down when the bottom of the ladder is 8 feet from the wall? Our strategy, like before, we'll find an equation relating x and h, differentiate both sides with respect to t, and then solve for dh dt. Let's give that a try. Give myself a little room here. So how are h and x related? Well, look at the picture on the right. I really have a right triangle where h and x are the legs, 16 is the hypotenuse, so it looks like h squared plus x squared equals 16 squared. Next step, take the derivative of both sides with respect to t. So I get 2h dh dt plus 2x dx dt equals 0. I can make my equation a little easier to work with by dividing both sides by 2. Let's identify what is it that I'm actually trying to solve for. Let's read the question again. How quickly is the top of the ladder sliding down? So it's that h. I want to know how h is changing. So dh dt. So I need to figure out values for h, for x, and for dx dt. Two of those I know right away. The x, because it says I want to know how quickly things are changing when the bottom of the ladder is 8 feet from the wall, so x is 8. dx dt, that's the rate of change of x, and that was given in the problem as 3. The last thing to figure out is what is the actual h? So when x is 8, what is h? So I can use the Pythagorean theorem and say that h squared plus 8 squared equals 16 squared and solve for h. And I won't go through the details, but it turns out that h equals 8 times the square root of 3. So here we go, 8 times the square root of 3. So I end up with the equation 8 square root of 3 dh dt plus 24 equals 0. So solve for dh dt, and I get negative 24 over 8 root 3, which is negative 3, over the square root of 3, which is negative the square root of 3. And that thing is approximately negative 1.7. What are the units here? I'm solving for dh dt, so the h on top, that's measured in feet, so feet, and the t on the bottom, that's seconds, so feet per second. So h is changing at negative 1.7 feet per second. Does that negative make sense? And yes, it does, because as x increases, that h is decreasing. So I do expect a negative number at the end. Now you have to be careful. Some problems are going to ask the question in a slightly tricky way. For example, look at this. It says, how quickly is the top of the ladder sliding down? So really, dh dt is negative 1.7, but we might answer this question with a positive number. The question is, how quickly is it moving? It is actually moving at a rate of 1.7 feet per second. Its speed is always 0 or positive, its speed is 1.7 feet per second. The last problem, a soccer goal. So this one's a little bit more complicated, but I think it's more interesting. We get to work with some angles in this one. Imagine a soccer player runs along the field toward the goal line as shown at a rate of 8 feet per second. So this soccer player is running in the direction of the arrow, he's getting closer to the goal line, he's running perpendicular to the goal line, and as he looks at the goal, there's an angle, theta. Now think about what happens when he's really far away, that angle is going to be very small. And then as he gets closer, that angle is going to widen up. But if he gets too close, if he goes right close to the goal line, the angle is going to close down again. So as he's running, the angle starts off very narrow, and then it widens up, and then it becomes narrow again. Now, while that is going on, it turns out that the distance between goalposts on a soccer field is 24 feet. And let's just imagine that he's running in a line that is 20 feet from the closest goalpost. And then lastly, we have x, defined as the distance that he is from his current position to the goal line. So we have 4 pieces of information. We have x, theta, 20, and 24. Here's the question. How quickly is angle theta changing when the player is 60 feet from the goal line? Is theta increasing? Is theta decreasing? First problem. How are x and theta related? I want to relate the quantities. Once I relate the quantities, then I can relate the rates and figure out information about rates. So pause the video at this point if you need to, and this is a little bit tricky, but think about it, see if you can do it. Can you make an equation that relates x and theta? When you are ready, unpause the video. Here we go, next slide. The first thing we might do is simplify the diagram. Get rid of all the stuff that doesn't really matter and take a look at only the stuff that matters. Now here's the trick. I'm going to label the other angle, and let's just call it, how about alpha? There we go, I'll call it alpha. Now I can figure out some tangents. It turns out that the tangent of alpha is 20 over x. And I can look at the angle that has everything. The tangent of alpha plus theta, that's 44 over x. Do you see what we will do next? Let's solve for alpha by taking tan inverse of both sides. Similarly, solve for alpha plus theta by taking the tan inverse of both sides. Now I can solve for theta. Theta is tan inverse of 44 over x minus tan inverse of 20 over x. That's kind of clever, right? And it's kind of curious. We end up with inverse trig functions in this relation. Now the next step. Now that we've related the quantities, now I need to differentiate both sides with respect to t to find out how their rates are related. So here's the equation that I just had from before. Theta is tan inverse of 44 over x minus tan inverse of 20 over x. We take the derivative of both sides with respect to t. And this one can be a little bit tricky. This is where some mistakes might creep in. The big thing to watch out for is that at the end of each expression I have a dx dt. It's like a chain rule that's actually 2 layers deep instead of the usual one. I start off by writing my derivative formula for tan inverse, and I put in the 44 over x, but then you think, oh, chain rule, I need to take the derivative of 44 over x. And so you get negative 44 over x squared. But don't stop, because x itself is still a function of t, and I'm taking my derivative with respect to t. So I need to continue and multiply times the derivative of x with respect to t. And that's where this last part comes from. Same thing on the rightmost term. Now let's multiply the fractions together. Here we go. But now each term has a common factor of dx dt, so let's factor that out. And I've simplified things a little bit by switching the order of the 2 terms on the inside. And at this point, I think I'm ready to start evaluating, right? I've found the equation that relates the 2 rates together. So what do I need to do now? I want to find how quickly is that theta changing when x is 60. So I'm going to plug in 60 for the x. And what will I plug in for dx dt? Now, he's running at 8 feet per second, but will I plug in 8? No, I will not plug in 8. I need to plug in negative 8, right? Yes, that is right. And when we do that substitution, it turns out that this answer is positive 0.024 radians per second. So it is increasing very slightly, but maybe the interesting thing for us is that we're at a point in this process where the angle is still increasing. I haven't passed that point yet. All right, and so that is related rates. These are fun problems that relate to quantities, and it's sort of curious to see how 2 quantities that are related have an equation that shows how their rates of change are related as well.